Hi guys, I've got a little job in. It's a bit grubby, come out of a shop somewhere, and it's a bit scratched as well. I'm guessing they might use it with a till or something like that, I don't know. It's just a VGA monitor, it's nothing amazing. I'd say it's probably one with an LCD backlight, a fluorescent backlight as well. It's not LED, I don't think. It says dead. So yeah, let's have a look at it. If we can fix it, you know, it's going to be like cheap enough to fix, and yeah, let's do it. I'm happy to have the money if they want to fix it. Okay, so let's open this up and let's look inside it and see what we can do with it. Okay, it's off. I basically have to prise it from under this edge, both sides, with enough force. You think it's going to break, and then it kind of like gives it up a little bit. You can get a spudger in between. I managed to destroy one spudger in the process, so I've broke the end off that one. It was tough, but eventually it's off. It's so tough I whipped up a sweat. I had to put the air conditioning on. So I've disconnected the ribbon cable, which has a plug which goes under here that I can't easily see, but it just unplugged. So that's fair enough. It's not like just the end of a ribbon; it's an actual plug. And then we have two wires, which I'm pretty sure must be for the LCD, the backlights, which are going down through here. But I'm not sure that I can actually disconnect them from here. They seem to just go into these little plastic things. Let's have a look to see if these actually unplug from here, or if I have to take this board out and unplug them from the other end. So what's this crazy little thing here? Is there some sort of connector? It might be. A bit hard to say, but there might be like a little clip here that maybe lets you flick this thing open. Something, yeah, there we go. Yeah, but it's just holding the wire down, yeah, so that yes, it's like a little plastic clip, but it didn't help in the slightest. So I'm going to have to unfasten this board, I think. But before I do that, there's going to be some high voltage in this, quite likely, because it sort of probably charged the capacitors up, and then nothing happened, yeah. So let's have a look at it for a minute and let's see what we've actually got here. So it looks like we have something insulated. This is kind of like this area here in this dashed line is the high voltage side, yeah. I can see that's clearly a bridge rectifier there. And then there's going to be some big capacitors here somewhere, which quite likely have some high voltage in. Because I know power went into it, but nothing happened. So one possibility, this will tell us if there is some voltage in here, but it won't tell us if there isn't. The reason being, this may have PFC. If I go directly across the bridge rectifier, if I read high voltage here, there's charging the capacitors. And I read 278 volts, yeah? So this doesn't have any PFC, and I have a high voltage here. So this is in a dangerous condition. So let's just zoom down and let's see how we're going to get rid of that. So to make this safe, I need to discharge the capacitors. And I'm not exactly sure where they are. That's not there. There we have the 275. Put the meter away, you can see it. This is the low voltage side. So there we have the 275 volts. Okay. And that must be going up to some big capacitors somewhere that I can't just quite figure out where they are because the board's upside down. Oh, here. Yeah, that's probably the capacitor. But that's where I have the high voltage. So the way to short this out is to use a resistor. This is a 3.3k resistor. A couple of stiff legs on it, and I can just literally hold this against the capacitor. And that will discharge the capacitor safely. So we won't get like a flash and a bang, which is not a good way to discharge a capacitor. But we can do it safely. So we can just fly. Obviously, as I say, summer's arrived, the flies arrived. So we'll just hold this resistor across here, this 3.3k resistor, for a few seconds. And this will discharge the capacitor safely. Okay, so if we come back now, we can see we now have about 1.8 volts, and the capacitor is recovering slightly, so the voltage goes up a little bit. once you remove the short, but it's only a couple of volts in here now. 0.7. Another thing this tells me, the fact I had a high voltage here that wasn't going away, is that there's no load connected from here. So after the rectifier, nothing's happening. There's nothing loading the capacitor. Now you would assume that in here is going to be a standby supply, yeah, and a main supply. So the standby supply comes on, and when you push the little button on the front, it switches on the main supply. But now we can get this circuit board out and we can actually have a look. So quite safely now I can start to undo the screws. Okay, so we can take this off. And then I want to just unplug these wires, which go from the inverter to the backlight. And then we can have a look to see what's wrong with our board. So we'll just take these all these screws out of here. Just take a minute or two. In fact, I'll pause it and I'll come back to you. Okay, so I've removed all the screws that hold that circuit board in. Again, we'll just check once more, but it should be fine across the bridge rectifier. And we have 4 volts, yeah, which is nothing. I mean, we can actually now short this out with a you know, with a bit of wire. You know, there's no voltage here anymore, basically. It's absolutely, it's gone now. Yeah. Not that the 4 volts was going to do any harm. So now we need to get this board out, and let's have a look to see how these are connected. And this is awkward because, and I can see straight away, there's a plug which goes down underneath here. So we've made, which probably goes to this, yeah, it does. So they've made this thing really difficult to get in. I think I'll show you, you can't see it. There's a plug under here that's stopping me from lifting this up, and there's plugs here that's stopping me from lifting this up. So maybe I'm going in at this the wrong way, or maybe it's just not an easy thing to work on. See if we can unplug some of these things. I can see the plug here, but I can't easily get it off. Oh. Give me 2 minutes. So I've got this off. So say this is your monitor, yeah. There's this little circuit board. You see now quite clearly where the screen plugs into it. So we can now get the this off here, yeah. And we've actually got down to the power supply board. And I'm sure this is where the problem lies. In fact, I know this is where the problem lies, because it's held a charge in the main capacitor, which it shouldn't do. So let's have a look to see what we've got here. Let's see if we can just work it out. I only see one main transformer here. So my idea that we have a startup supply and we have a main supply is probably not correct. You can see the dashed line again. So this is where your high voltage side is, all inside here. Yeah. And then this is your transformer, this is your opto isolator. I'll just zoom it down, you'll be able to see them better. There you have it. So as I say, this is all the high voltage side within the dashed line. And the transformer bridges the gap from the high voltage to the low voltage, and so does the opto isolator. And a couple of high voltage capacitors, you sometimes find this as well. So yes, there we have it. This chip here and this chip here, I suspect, are driving these. So these are the 2 inverters that drive the fluorescent tubes, which is the backlight. So that's what those are. Now, the first thing I notice is there's a capacitor here that's gone. Yeah, that one there, it's got like a, it's gone, yeah. And in fact, this one's gone and this one's gone. Can you see the like bulbs? I'll probably be able to show you even better than that. If I just bring this all the way down, let's just get to it. There we go. Okay. So we have 1, 2, 3, And looking at them closely now, this one's bulged on the top as well, even though it isn't gone. You can see it's like concave. This one kind of looks all right, but I don't trust it particularly. And this one's gone. This one looks kind of okay, and these two are gone. So we've got 4 capacitors at least that are gone on this. There's also another one here that looks okay, and that's basically what we have. Now I suspect, oh yeah, another little one here. I can tell this power supply was not starting. If it started, there wouldn't have been a high voltage in this capacitor, and there was. So the first thing I'm going to do with this is replace these capacitors on the secondary, on the low voltage side, all these ones. But I don't believe that would actually stop this from powering up. I'm more inclined that there's probably this little capacitor might be involved with that as well. Let's see if we can see the controller for the power supply. So there's a few things on the other side of the board, and straight away here I see a chip, and this chip is within the high voltage area, so this is quite possibly the controller that's effectively starting all this up. Yeah, the pulse width modulator that's driving this big MOSFET, most likely could be a transistor, and driving the transformer. So we may have to look around there for the startup circuit, and we'll do that by finding a data sheet for this and seeing what this chip is. But before we do any of that, let me remove these obviously bad capacitors and let me change them. Okay, I've replaced the ones that were bulged. So I've used some salvage ones, but I've checked the salvage ones on the capacitance meter and also on the ESR meter, and they're good. So these are 470 microfarad 25 volts, which is what we're originally in there. This is a 1000 microfarad 10, but I've actually put a 1000 microfarad 16 in there. They're all 105 degrees C, and they all have a very low ESR on the meter. So I've done that. I'm now going to check this one, and these two small ones. Although they look okay, because I've had 4 visibly bad capacitors on this, I think it's worthwhile checking the other ones. So I'll have a look at those, and if I find anything interesting, I'll let you guys know in a minute. These tested okay. You also notice I've marked on the board the value as well. I took them all off at the same time to test, so just so I know what went where. This one actually here also read okay, but it's the same brand. This is one of the bulge ones actually, but the one that was here is a slightly smaller one. I put it in the bin now, but it was the same brand as 3 of those that had failed. So I thought, well, while it was off the board, I just stuck another one, and this tests okay for ESR and for capacitance, as did the one that I took off, to be honest. So that's the capacitors replaced. So I think what we'll do with this now is we'll try and power this up and see what it does. Now, probably the easiest way to test this without it connected to the monitor is going to be just to power it up, and if I just hang my oscilloscope probe somewhere near to the switch mode transformer, if it's working, I'll see like pulses. I don't need to touch it, I just need to hold it near to it, and that'll see if it powers up enough. Sorry, if it powers up. The other way is probably to switch it on and off and see if this capacitor discharges. Obviously then it's drawing power. But let's just see if we can just detect this on the oscilloscope without actually touching it. So I'll just get that ready, then we'll give it a try. Okay guys, so this is ready to go. I've just put the camera so you can see the light bulb up here. This is the current limit. So I'm just going to switch this back onto limit. And I don't actually think that changing these capacitors will have fixed this, because they were all on the secondary, and I don't really believe that those 40 capacitors would have stopped this from running in the way that it is. In other words, it doesn't even seem to start. These 2 little capacitors might have caused that, or one of them might have caused that, but they checked okay. So let's see if it does the same before, which is like the light bulb flashes once and then goes off. So we'll just power it up and let's see what it actually does. Yeah, so it's done the same as before. I can switch it to mains power now, and if I hold my scope probe, I'll just get onto the scope, which is here. So I hold the scope probe near to the transformer, all you can see is like low frequency noise there. Yeah, that's just like low frequency, mains frequency, noise. If it was running, you would see a lot of very high frequency pulses there, yeah, just by holding it near. So I've got no ground attached to it, I'm just effectively sensing it. So we switch this off and we'll take our multimeter now on volts, and I'm sure we'll find that the main capacitor, which is here, has got a very high voltage charge in it. It's in a dangerous condition again. So the power's off. I'm just going to go across this capacitor, and yeah, look at that, 320 volts nearly, yeah. That is enough possibly to kill you, actually. So this is why you need to take care when you're working on a power supply such as this. This is the pulse width modulator controller chip. This is driving the MOSFET or transistor that drives the main transformer. So this is controlling the power supply. You can see it's an LD7522PS. That's the part number. So let's have a look for a data sheet for this and let's see how it actually works. I'll just go over to the Windows desktop. Okay, so this is the data sheet. And it tells us it's a pulse width modulator controller. And we can see the chip here. So this gives us a kind of typical application. And we can see from the positive end of the bridge rectifier through the primary of the transformer, it goes to one end of the main power MOSFET, and the other end goes via a current sensing resistor to ground. So we can see that. The chip has VCC, which is the power, and this has a few other pins as well. So we can have a look at the chip. This is the one. The letters afterwards is just a package, basically. So we can see we have VCC as the power supply pin. We have BNO, which is saying brownout protection pin. It's saying connect a resistor divider from this pin to the bulk capacitor. Bulk capacitor means the big electrolytic after the bridge rectifier. So we connect to the positive of this, and it's saying that if the voltage on this pin is less than a certain threshold, it'll shut off. Okay. We have current sense, outputs, and such like. And we can have a look. This gives us some parameters. So we can see, let's first have a look what power supply this thing requires. In fact, no, while I'm at it, I found brownout protection. This is the BNO pin. So it's saying that if the pin typically has 1 1/4 volts on, it's turned on. And if it has 1.10 or less, it's turned off. So that pin needs to have more than 1.1, probably 1.25 on there. So we can find that one. Let's have a look at the power supply voltage to see what it should be. Let's say supply voltage VCC. So it's saying this is startup current. Does it give me the voltage for it? Oh, suggesting under voltage. Right, okay. So it should be more than 16 volt supply. Otherwise, you get an under voltage lockout and it switches off if it's less than 10. So again, we know that the power supply pin needs to be more than 16. Is there a maximum? Yeah, and the maximum is 17. So that gives us a very good idea of what the supply voltage should be. I think that's all we really need to know from this chip. So we can actually have a look around. I think now before powering it up, let's just check that this circuit here effectively is intact on our board. So we can see from the positive of the bridge rectifier, and we can use the resistance meter, we should have a connection through here to the MOSFET. So that's the power should get into the MOSFET. From the other side of the MOSFET, we should have going to ground a low resistance, maybe just a couple of ohms or an ohm, or maybe a bit less than an ohm. That's the current sense resistance. So we can check if that's basically that circuit is intact. We know that the bridge rectifier is working because we know we get about 320 volts here charged up, but nothing discharges it, leaving it in a dangerous condition. So because nothing's discharging it, either there's an open circuit somewhere down this path, or this MOSFET has never been switched on. Okay, let's go back over to our board and let's have a look to see what we have. Okay, so this is the large capacitor. which is holding a charge, and this is the positive end of it. So if we check from here, we should have a connection to the MOSFET down here on one end of it or the other. I would say on the middle pin. Yeah, and we have about 1 ohm to there. This is marked, I can actually see G for gate. You might not quite see, but it says G, D for drain, and S for source. So we go to the S for source, which is this pin. This should go back to the negative of this large capacitor. And it does. So you can see that circuit's intact. In fact, I'm pretty sure we can see it a little bit better even on the other side of the board. So, yeah, let's have a look. So this is the capacitor we were checking across. And if we just look at this, you can see that it goes through a resistor here. And that ends up one way or another on here. It looks like there's a oh yes, through a resistor here to the primary of the transformer, and that goes to the middle pin of our MOSFET. So that's where we were measuring a low resistance, and it's actually going through this resistor. We can see. So this will be the same as on the other side, 1.3 ohms. And my meter when it's 0 reads 0.7, so it's about 0.6 of an ohm. And from the other end of the MOSFET, which is here, we can see it goes again through a resistor with the current sense resistor and back to the negative of the large capacitor, the bulk capacitor as these are calling it. So we know those resistors are good, we know that circuit's there, so we can say now with a good degree of certainty that this MOSFET has never been turned on. So now we need to look at the controller chip, and the first thing we want to see is, has this chip got power? Has it got VCC? So we'll double check which pin VCC was on. In fact, I'll probably just print that as a data sheet so we can see it. And then we can have a look around this and see what we've got. To make things easier and a little bit safer, I've just tagged a piece of wire onto the negative end of the bridge rectifier. So this is not ground. This is the point of reference for the high voltage side, but it's not a safety ground. So basically that negative end of the bridge rectifier, depending on the half cycle of the mains, is either connected to the live or the neutral, alternatively, yeah. This is our chip which we're interested in. So the wire I've tagged on, I'm just going to connect a crocodile clip and just attach this to the meter. So that means now I've got one hand perfectly free to work on this, and the other hand I don't need to use. So it's best when you're working on high voltage stuff only to effectively use one hand, put the other one on, you know, in your pocket or somewhere. Yeah. So if you look here, this is the actual chip, and I've just shined a bit of light on it. You can clearly see pin 1 is where the little dot is. So according to the data sheet, we have VCC on pin 7, and this is the first place I'm interested in checking. Does this chip have any power? You can see pin 7 is here, yeah, but you can also see it goes to this capacitor here, which is a nice easy place to attach. I'm assuming that's a capacitor. So I can hold the probe on here now, and I can actually switch the power on, and then it's connected through the light bulb current limiter again, so you just get a little flash on the bulb, and if I slip, nothing's going to go bang basically there. So we switch on, and we can see we have 12. Can you see that's going between 12 and 13 volts, yeah? This is fairly typical of where the chip is actually trying to start up. So that voltage is going up, down, up, down, up, down. That suggests the chip is trying to run, but something is preventing it from running. Now you can see, once again, I've switched the power off, but on the main bridge rectifier, or the large capacitor, just get it into view again here. This is my bit of wire. This is the bridge rectifier. We have 283 volts here, so this is this dangerous condition we have. But it looks like that controller chip is trying to switch on and then switching back off again. Let me just explain to you how I know this chip is trying to start up and isn't starting up, and what could be causing the problem. So basically, there'll be a high value resistor, probably this one. In fact, I'm certain it will be this one. A high value resistor and a capacitor here, you can see. And the idea is that when you power it up, the mains voltage through this resistor charges this capacitor. And when it charges up to a sufficient voltage for this to switch on, this starts to oscillate, okay? This is a Zener diode, and this will be effectively set between that and this resistor to limit the voltage, so this can only charge up to a certain amount, at which point this starts to conduct. Okay. Now this capacitor, when it charges up, reaches a certain threshold voltage, and then this switches on. Okay. Now the way this circuit is designed, and these are always designed this way, is this resistor cannot itself deliver enough current to keep this running. So once this switches on, it starts to discharge this capacitor because it's drawing current from the capacitor to run. This can't supply enough current. So after maybe a second or whatever, the circuit's designed, second, a couple seconds, whatever, the voltage here will drop to the point where this switches back off again. When this switches off, it's no longer drawing any current. So the resistor again can charge the capacitor and it switches back on. And that's what this is doing. It's cycling between on and off, on and off. Now what's supposed to happen in normal operation is that once this starts, it starts driving pulses to the gate of the MOSFET, which is pulling current through here and effectively turning the power supply on. Now you'll see here, this is a secondary of the power supply, but look, there's another secondary here. Although it's shown on this side of the schematic, it is a secondary. And this secondary goes via another diode, which will be a Schottky diode. It's a slightly different symbol if you look to that one, more like a letter S. This is a Schottky diode, and this Schottky diode charges up this capacitor. So once this starts running, and this is now pulsing, and this is starting to work, the power generated into this secondary charges the capacitor. In fact, it's charging two capacitors and through two diodes as well. So this supply can supply enough current to keep this running, and this stays running. And as long as this is providing power, this will keep on running. So that's how the circuit should work. What we have is a situation where this is working, charging the capacitor, this is turning on, but this supply never comes on. You never get anything from here, so hence this is switching on and off, because as I say, this cannot supply enough current to keep this running. Now, there's a few possible reasons why this may occur. I mean, if this MOSFET is effectively open circuit, so it never switches on, that would happen. Okay. But another good reason why this would occur, and bear in mind we could have a fault here, or possibly a short circuit capacitor here because this is reverse biased, so it wouldn't stop this charging up. So there's a few possibilities: open circuit resistor, open circuit diode. But the more likely and common one is that this secondary has a short circuit. So as soon as this tries to run, it's just running into a short circuit. So that's what I'm going to check next on our supply to see if there's a short circuit on the secondary of the transformer, or secondaries if there's more than one. So here's our power supply, and we can see the MOSFET, the transformer. So the transformer secondaries are on this side. And straight away we can see two big power devices here. And these will be diodes, double diodes. So if you look, there's three legs on each one, but each one actually contains a diode, and they're marked D606 and D603. So this has two secondaries, and it's possible we've got a short circuit on one or both of them. So let's have a look under the board. Okay, I hope you can see clearly now that, so this one, we have the two outer pins are basically connected together, and then the middle pin is the output, if you like, the cathode of the diodes. And there's two diodes in this package in parallel with each other. And then we have the same thing here, so the two outer ones are connected together, and this is the output. And we can just prove that if we just go on the resistance. The two outside pins are connected together on both of them. So we can just consider it to be a diode in and out, okay? What we're interested in is what's happening on the output. So this is the output of this one, and this clearly is ground. Do we have a short? And yes, we do have a short, or very close to a short. This is the output of the other one, and again, this is ground. Do we have a short? No, we don't have a short. So we know now the reason our power supply is not working is because there's a short on the output of this diode. Yeah? Is the diode itself short? Let's have a look. So, yes, it looks like it is. It reads both ways the same, yeah? Whereas this one doesn't read. In fact, you just get a capacitor charge, yeah? So it looks like there's a short circuit in this diode itself. Okay? So the first thing I'm going to do is actually remove the diode. That actually may not be the case, actually. There's a short circuit in this diode, because this end of the diode is connected. Yeah, look, we can't say that's short. This end of the diode goes to the secondary of the transformer, and the other side of the secondary transformer goes to ground. So there's no way to say whether or not that diode is short unless we remove the diode first. So I'm going to go ahead and take the diode out, and if the short is still there, then let's trace it to see what it supplies and see if we can find where the short is. I didn't actually have to totally remove the diode to test whether it's good or bad. I've just unsoldered the pins, so it's still in the board, but you can now see the middle pin is unsoldered. In fact, I've unsoldered all of them. So if we now go on the output of here to ground, we still have a short circuit. Well, if we go to the actual pin of the diode, we don't, yeah? And not only that, if I actually measure across the pins of the diode, you can actually see the voltage drop, 0.3, so this is a Schottky diode. So we know that's actually good. So the short circuit is somewhere that this is driving, whatever this is supplying, yeah? So what we now need to do is trace to see where that actually goes and see if we can find something that's short. I mean, we could stick some voltage in this and just see what gets hot, but on a board like this, which is just a single-sided board, it's not difficult to trace it to see where it goes and start unsoldering things. So let's have a look around to see where this actually supplies and see if we can find where the short is. We can see that this power supply basically supplies whatever this was connected to, but it's now disconnected, so the short can't be down there, yeah? And we can disconnect, this is the little, effectively the video driver, so we can disconnect that. So we can now see, is the short still on our board? And if it is, it's something on here that's short. So let's have a look. Yeah, there's still a short there. We still have a short circuit. So the short's on here somewhere. And the thing this drives basically is the inverters for the backlights. So these are the inverter coils, and these are your backlights. It's called an inverter because it's an AC signal. It generates a high frequency alternating current, not DC. That's why this is an inverter, okay? And this inverter looks like it goes to this chip, and this inverter looks like it goes to this chip. So it's looking like we have two, and this one looks rather kind of like it's a bit burnt around here, yeah. So I think the first thing we'll do is just take this chip off the board. I mean, I could use a low ohms meter and start to trace it round, but there's a good indication that this one has been running hot, which maybe this is where the short is. We can see pretty much if we're on the right track. If we just go to ground and we go around these two chips, yeah, do we see a short around them? So this is the one which is looking rather hot. One pin's going to be ground anyway, but this chip looks like there's a lot of shorts around it, yeah. I think almost all the pins are shorted. This might look the same because they're in parallel. I would think they're in parallel. Yeah, so it's looking about really like pretty much the same. Well, that pin reads different. No, it reads different on both of them. I'm going to take the one here off the board first, and let's see if that is what's a short circuit. I've added some leaded solder to all the pins to reduce the melting point. And you could use solder braid, but by far the easiest way to do this is one of these things. It was really invaluable for this sort of work, so if you don't have one, this should go on your shopping list. one of these will more than pay for itself, even if you're just doing repair work as a hobbyist. You can see how easily this is dealing with this. Put solder braid, or if you're using solder braid, put some flux as well. One more. And that pit, that chip now will just literally fall out of the board. So, yeah, it's off. Yeah. If you do buy one of these, once you've used this, it's important always to clean it afterwards. If you clean it now, it won't clog up on you, or it'll be very unlikely to. If you let it clog up on you, then you in for a lot of problems. In fact, it's slightly clogged now. So what we do is we'll take this and push it through. Yeah, there you go. If you'd let that cool down, that would have been a real problem to get that clean again. Okay, it's clean now. It's going in and out clean. Okay, and I can hear the sound of the air hissing through it. Okay, so we've got our chip off the board. Have we got rid of the short circuit? Has the short gone? So again, from the output of the diode to ground. I put the meter where you can see it. I think you just saw it anyway. So yeah, the short's gone. So that chip is definitely the problem. This is our problem. Let's have a look to see what this part is. In fact, you can probably see now where it has overheated, and this one looks nice and clean. Let's have a look under the microscope and see what this part actually is. There's the part number then, so it's 9971GD. I think there was probably like a date code or something similar. We can look at the other one. Yeah, 9971GD. So that's short. Now there's a possibility that this has gone short because of a problem with the transformer, the actual transformer in the inverter. So we might just be able to prove that before we go around looking for parts. This is the inverter transformer, and you can see we have effectively 3 terminals here. So these are two and two. You can see they've got wide traces connected together, and this will probably read basically like a short circuit because the windings will be a low resistance. So you probably can't see a lot of difference with the meter, and we can compare that with the other one. So let's have a look where the other one is. Here it's mounted sort of sideways. See, that's reading 12. Yeah, it's gone down to about 6 now, and that's reading about the same. If we go across from the secondary to primary, yeah, we got about 2.1 meg there. And then we can just check the other winding. It reads about 0.49. Okay, let's have a look at the one where we had the voltage chip. So it's here. So that's reading about the same on there. If we go from the primary to the secondary, 0.9 of a meg. I think the way might read about 2.1. Yeah, 2.1. So that reads about the same. And then these, yeah, read about the same. We could use the low ohms meter, but I'm pretty confident that both of these transformers are okay. And the other reason, apart from the fact they read basically the same as each other, is that if you've got a shorted turn or something in one of these, the thing is going to look distressed. Yeah, it's likely to burn up or overheat, and I'm sure you would see some signs of stress if that was actually faulty, or anything on the secondary. Then you'd see something. This is a very high voltage AC signal, something's going to burn up. So I think we can say with a great degree of confidence that if we replace this chip, this is going to work. Let's have a look to see if we can get any of these things. I looked for a data sheet for this, and in actual fact this chip is a dual MOSFET. So we can see if we just go over to the browser again. This is the actual chip. So you have gate 1, source 1 and drain 1. So those pins, 4 pins there, make one MOSFET, and then gate 2, source 2 and drain 2 make the other MOSFET. So in here is 2 MOSFETs. So if we have a look at the one I've just removed from the board, we can actually see what's happened to this. So this is the chip, yeah, and this is one of the gates, and that's short to the source, and this is the drain, so that is all short. This is the other one, and this doesn't have any shorts. So one of the MOSFETs here is completely short. So I think because of that, we need to go a little bit further back and have a look to see what's driving these. Is there anything else that's obviously damaged? So if we go along to the other side of the board, you'll see there's another chip, this one here. So I'm going to have a look at this one. This clearly will be driving these two dual MOSFETs. And I want to have a bit of a look around here. I'm interested, is there any gate resistors in all the open circuit? And secondly, just having a look around this chip, can I see anything obvious here that is saying this might be faulty? So the first thing again with this one is what's the part number, and I'll just get I can sort of see it, but I'll get the microscope and let's have a quick look again to see what this actually is. So we'll just go over to the microscope camera, and this is our chip. I'll just get it into view there. Okay, so this is the chip. Some focus. Let's have a see what this is. A bit hard to read, that's what this is. Oh, I've got it now. A bit hard to read, but I'll look down the microscope and see if I can get a part number from this one. Sometimes it's easier for me. Oh, you can probably see it now. INL837G. Can you see it? It's INL837G. Let's look at the datasheet for this one and see if there's any more measurements we can take. I couldn't spot a full datasheet for this, but I did find the information I need. So once again over to Windows browser. So this is the chip, and you can see straight away that pin 1 and pin 16 say drive 1, DRV1, DRV2. So I think we can say with a good degree of confidence that these are driving the two gates. And because there's one of these chips, it's probably driving both of those sets of MOSFETs in parallel. So let's have a look again at the one on our board. Here we are. So this is pin 1. This is the one I've unsoldered, and pins 2 and 4 are the gates. So you'd expect pins 1 and 14 to go to the gates. So this is one of the gates, and that goes to pin 1. Yeah, just pin 1, not 14, obviously. That goes to pin 1, and it's reading 2.6 ohms, and with my meter 0, I'm getting 0.1. So there appears to be about a 2 ohm resistor there somewhere. Looks like it's here actually. Looks like that's the resistor. So that's reading there. And what do I get going to the other one, the other chip, which is just a little bit over this way? Here it is again, so let's just go. So pin 2. Yeah, about the same, okay. So it looks like they're either both coming through the same resistor, in which case they'll be connected together, or more likely there's two resistors. Yeah, they're both connected together. I'm actually connecting from one to the other. So they're both connected together, and the resistor looks all right to me. And this is pin 4 again, so this goes to 14. And that reads about the same sort of resistance, yeah, and that will go to the other chip as well. Pin 4, and again, they both seem to be connected together. Yeah, so we can say with confidence, I think, that the gate drive resistor is probably okay. They both read the same on each of the pairs of MOSFETs, and they both go to both chips. But I think it's probably reasonable that we see if we can order, if they're cheap enough, we get these as well. So I'm now going to look for both parts and see if it's worth repairing this thing. Let's have a look. Okay guys, I've had a quick look on AliExpress. So the INL837GN, I can get 5 of them, €2.78 plus 145 postage, is about €4.20. And the double MOSFETs, I can get 4 for about €1.70. So yeah, like €6. And bear in mind, that's including VAT, and I don't have to pay the VAT, so I get 21% off that, so be just under €5. So yeah, I think that's well worth ordering, and we can see if we can repair this one. Okay guys, so that's it really. I mean, I've been recently trying to actually, you know, order parts and wait and publish these videos a little bit later when the parts arrive, so you can see that they are working. But I think in this case, it's very, very likely that this will solve the problem. Yeah, and I can see another resistor down here that looks a little bit heated, and we can test that. We can just I'll just tell you now. I'll just do it on my own meter. What is his reading? 99 ohms. I can check the value of that one. But I think really that we proved where the short circuit is. If it needs a resistor, it needs a resistor. But I'm happy to order the parts for this, and I think it's going to be worth fixing. Okay guys, so I hope you learnt something from that. You can see we were tracing the problem from the fact the power supply didn't start up at all, hence the very high dangerous voltage in the capacitor, through the fact we can see this is trying to start. And I hope you can see, if you didn't know about this, the way this circuit works and how I knew from that this wasn't starting up. And then onwards to the short circuit on one of the secondaries, and there we have it. Okay, so I hope you enjoyed this video. Let me know if you think I should have waited and published this in about 6 weeks' time when the bits arrive. I will get into the comments below when they are and just come up with an update on this. If it doesn't work, then I'll make a follow-up. So I'll see you all soon on another video, and enjoy yourselves. Ciao for now, guys.